Okay, so now we're going to kind of talk more about our density curves, but we're not going to call them density curves anymore. We'll call them our normal curves or normal distributions. So one particularly important class of density curves are normal curves, which are described by a normal distribution. So we capitalize the n in normal because they're not normal at all. They're not usual or typical. They're very special. So they show that with capitalizing it. So all normal curves are symmetric, they're single peaked, and they are bell shaped. A specific normal curve is described by giving its mean, mu, and standard deviation, sigma. So we're going to stay away from x bar and s of x to describe mean and standard deviation on a normal curve. So I know we had that question in class the other day. So and we'll focus more too on mu and sigma because we're getting into population shortly. So the mean and the center are the same on your normal distribution because it's symmetric. Changing your mean without changing your standard deviation. So we saw shifting and scaling in class. So changing your mean without changing your standard deviation will move the normal curve along the horizontal axis, but it's not going to change its spread. So the standard deviation is what controls the spread. So this graph right here, this normal curve right here obviously has a larger standard deviation. This one has a smaller standard deviation. That's why this is bunched closer together. Actually, I'm going to stay on this for a second. So, because of this, your standard deviation, your mean and your standard deviation completely decide the shape of your normal curve. We can also locate your standard deviation by eye. It's kind of weird, but if you kind of trace it, you can feel where your curve starts to change its curvature. And that's where each new standard deviation comes in. So if you take a pencil and you trace it, you kind of feel where, because you guys have this in front of you, you kind of feel where the curvature starts to and that's where your standard deviations lie. So I think some of you may have heard the word inflection points in other math classes. So that's exactly what they are. Okay, so a normal distribution is described by a normal density curve. Any particular normal distribution is completely specified by two numbers, its mean and standard deviation. The mean of a normal distribution is the center. The standard deviation and where is the distance from the center, and it's where your curvature points are. We abbreviate your normal distribution as a capital N, and in parentheses, you'll first notate its mean and then its standard deviation. So normal distributions are good descriptions for some distributions of real data. So typical is like your test scores. That's where that bell curve comes in. Normal distributions are good approximations of results of many kinds of chance outcomes. Many statistical inference procedures are based on normal distributions. It's like all we do from chapter 17 to the end of the book. So then why are normal distributions important in statistics? Well, for kind of three reasons. One, normal distributions are good descriptions for the set of data. So for example, scores on tests, by taking many people. So whether you're talking about SATs versus all of my geometry classes. Repeated careful measurements of same quantity. Okay, so constantly taking the diameter of a tennis ball. Characteristics of a biological population, such as the lengths of cricket and yields of corn. They're good approximations for the results of many kinds of chance outcomes, like the number of heads in many tosses of a fair coin. So we'll look at things like 500 different tosses and see if it fits a normal distribution. And then we see that many statistical inference procedures. So we'll be using a normal curve to be able to find different probabilities and the likeliness of events occurring. Okay, so I'm actually going to cut this off at this video, guys, and keep going. Start up a new one for the next.